Our next speaker is Professor Zachary Kingston, who is new faculty at the Department of Computer Science at Purdue, where he leads the Computational Motion, Manipulation, and Autonomy Lab. Zach has worked on some of the sort of foundational early test and motion planning work with IDTMP. He's worked on a lot of motion planning under constraints and hardware accelerated motion planning, whole range of topics. He is also an OMPL maintainer, so we will be taking bug reports as well as questions if you have any. But yeah, today we're going to hear about some recent work on bridging the gap between language, constraints, and task and motion planning.
I think I'm sharing my wrong screen. 1 second. Let me figure this out. Also, on the OMPL comment, you can pip install OMPL now. I never want to see another Python binding issue ever again. All right, I think I'm sharing my screen. Should be good. All right. Well, hi everyone. Yes, I'm Zach, and let me make this a little bit smaller too. Okay. And so if you don't understand the, let's say the, what the title has here, it's, you can replace either there. So speaking plainly or speaking planly. Anyway, silly little joke, but I think basically the concept of today's talk that I want to talk about is, when you're communicating with a robot and maybe you're communicating with some sort of underlying, like some task motion planning, some sort of reasoning system, what you're trying to do is you're telling the robot, I want you to do this way, and I have some objective for you to accomplish, but there's also some things I don't want you to do. There's some things that I want to impose upon how you're going to be doing that. And that is kind of passed along to, you have some sort of high level, reasoning framework or something like this that's kind of coming up with the high level actions. Maybe you have something that's then generating the motion. And then each of those is complaining at each other and telling each other what they want each one to do. And then eventually the robot will try to figure out how to make that happen at somewhere at the end of the line. Or maybe it's not going to be able to do it. And I guess the too long didn't read or too long didn't listen to this talk, you can go on your laptops now, is that constraints and some way of expressing these kinds of constraints is the lingua franca for all the different parts of your task and motion planning stack. So at the planning level, at the interaction level with the human, and then eventually at the motion generation level, all the way down. So, when we're talking about this, let me maybe ground it with a specific example. Some people kind of talk about this idealized as like, oh, robot, I want you to wash the dishes. And then the robot will somehow be like, okay, well, then I need to wash dish A, wash dish B, so on and so forth. And, in order to support my hypothesis of, constraints are the way that people communicate, I went to YouTube and typed in how to load a dishwasher. And I collected a set of thumbnails that I think kind of illustrate how maybe people actually communicate about these things, right? And so it is a variety of telling you what not to do and support of actually trying to get you to do the thing that you actually want the system to do. The system in this case, I guess, is, you having now you have a home now that you're a professor and things like that. So you're no longer washing dishes by hand, things like that. So maybe a more realistic situation of robot middle management is, you ask the robot, tell it to do a bunch of things. You tell it, okay, but I don't want you to do this. Okay, this is new. I want you to wash this by hand, so on and so forth. And the robot's probably going to get a little bit confused because this is a whole lot of things that you want to throw at it in order to specify how you want to do the task. And I think that, I was actually really happy with some of the comments that Animesh was making in his talk, talking about how, different, kinds of the different tasks and the complexity of tasks that are being actually asked of robots. And so here are a couple of examples. I think Jeanette gave a talk in the morning, unfortunately wasn't able to come, running another workshop over on the other side of the hall. But TidyBot here, where you have the robot going around picking up trash, clothes, and things like that, distributing it around. And there was also this one, Look Before You Leap, where you see the Franca doing things like pour chips or, pick fresh fruits or something like this, where you're describing these kinds of very high level descriptions of things. And the robot now magically is able to do these types of tasks. And so kind of the thing that's really of interest to me, kind of going down this whole idea of constraints, is like, what is actually, the name of this workshop is Language and Semantics and TAMP. So what are the language and semantics of the types of tasks that we're actually asking these things to do? And so if you take a look at, for example, this is Palm E on the left and do as the SECAN paper on the right, and you take a look at the types of natural language queries that they were actually concerned with. Right. And so these are very much, you move an object to another location, you go, there's a lot of semantic grounding here, like move banana to Germany and things like this, where it requires you grounding to some sort of visual signals in the scene. And then over here, you can see the types of long horizon tasks that they're considering is like, oh, I spilled a Coke, throw it away and bring something for me to clean, where a lot of the difficulty there is just grounding semantically that very abstract statement. And so kind of what I want to talk about is like the tasks here are not actually interesting from a task planning perspective, right? In kind of the sense of traditional AI planning, what are the types of domains that people are looking at that are actually have really complex behavior? This, Animesh brought this up at the end. What are complex tasks? What do these domains have? What properties do they have? And so I came up with a list of some things that I think a lot of these domains have. Like I said, no shade to TidyBot. I think it's a great paper, but it has a rather simple task that it's trying to do. And the properties of these tasks are things like monotonicity, right? Every action that you do is going to bring you closer to the goal. There's nothing that you can really do that's going to take you too far away. I can always just pick something up, put it somewhere else. I'm no farther away to solving my goal than I was before. These domains can be ergodic, which means that, I can just kind of randomly move around the space. I can kind of reach every possible, anywhere I could be in the task planning position. I can just do things and things are fine. Invertible, I can just undo my actions. If I do something wrong, I can just pick it up and put it down somewhere else again. I have a nice local search topology. And what that means is that I can take a look at what actions I have available to me right now. And there's usually something better that I can do. Like I can see that, oh, taking this will actually lead to progress for reaching my goal. They're decomposable. I mean, we've seen quite a few examples of this where a task can be broken down into subtasks rather easily. If this is the case where you have composability in your task, that is also important. And also limited subtask interference. So when I do break down my task into subtasks, these don't actually trip on each other's toes. So, throwing away one thing is not going to cause me to now be impossible to then put away the laundry or something of this, something like this. And I think a lot of the types of tasks that you see, and I think like maybe one thing that I'd like you to take away from this is that when you're looking at a TAMP paper or a reasoning paper, do the domains that, are the tasks that people are looking at, do they have these properties, right? Or are you doing something that really has some sort of complexity to it, right? Something really, really deep in the search problem. And I kind of want to just illustrate some examples of maybe some undersold cases where TAMP, I think, is really important, like where you don't have necessarily these properties. So things like, sorry for the contrast, but there's this excellent paper, Assemble Them All, and we're doing assembly planning, where there's this long horizon sequence of, you have to be assembling these really tight widgets. There's a lot of physical interactions and things like this. This is a really complex search problem. Same thing, here's an excellent video from a company, Bot Built, where they're assembling frames of houses. Right. And so this is a very complex task and motion planning problem that they need to solve in order to assemble these things. And I think it actually has a lot of, the types of constraints. There's a lot of things that you want to make sure are done very properly that satisfy things, because you don't want to build a house where, I don't know, would you trust an LLM to build your house at this point? Probably not. But, and then there's some examples from my own work where I think you have these really complex geometric interactions where it's not immediately clear what my best action is to take because it's something implicit in the geometry or implicit in how things interact in the scene. So this have to fetch this little thing out this puzzle box. There's also work from Robonaut moving around. And I'll just skip straight to the good part of the actual video of Robonaut moving around, where this is a very long horizon, complex reasoning problem where we're just tasking it to go to the end goal. There wasn't any LLMs or anything like that at this point, but I think this illustrates a lot of the types of properties that I think are interesting in a lot of task and motion planning problems that are kind of undersold in a lot of tabletop manipulation and other kinds of domains where the task and the geometric elements are not as hard. So yeah, we can let it play out. I can skip ahead. Yay, it opens the valve, skips it ahead, pushes it out the way, goes, eventually gets over there. Wow, cool. So I think this is like an example of, some of the types of stuff that I would like to see real, other humanoids doing, things like that, actually moving around, reasoning, interacting with, tough physical objects. Okay, so kind of getting into how do you then generate the plans for these things, right? So, some of the stuff we've talked about LLMs as, the direct planners. So generating the actions that we would like. And, these are really great at the semantic and common sense reasoning, but they're not so good at these types of constraints that I've been trying to emphasize, right? So this is well known in the literature. You can go find a million position papers on arXiv talking about how they can't plan. The examples of, for example, go from blocks world, and then you start talking about it's no longer blocks. You're talking about gleeps, and you can glorp them, and so on and so forth. You kind of anonymize the domain, And then now it can no longer reason because those don't really exist in the training data set. And one of the ways that people kind of get around, kind of the longer horizon reasoning aspects of this is that you can kind of break down the problem, doing this this subtask reasoning. And so, you can have this abstract planning space. Let's think about I'm currently describing my scene. This is what I'm looking at. And then I ask my LLM to break down my goal. So I'm trying to get over to the top right. I break it down to sub goals. And then, I kind of move around. I can kind of guide my search through the space, moving from sub goal to sub goal. But when you have these types of more complex constraints, so the things I've been talking about of, maybe stuff like, you don't want to, do some of the stuff listed above, right? Things that are impossible for your robot to do, right? These are, this is kind of an obstacle in this planning space. The sub goal breakdown doesn't really work. You need to have some sort of more holistic search, have some way of actually reasoning over this. And I think, chain of thought stuff's kind of getting here, but I don't think it really solves the whole problem. And the other approach, Animesh briefly mentioned this. I think this is an excellent paper of where they're doing large language models to translate to chemistry robots and things like this, where they're actually translating to a formal specification here. So that's the paper on the right. And as you said, you just take the language model to then ground to an actual domain, right? And then you hand it off to a task some sort of geometric or some other solver that has some knowledge of the skills and so on and so forth about how to compose things together. But the thing here is that if you don't have a good definition of your domain or how to ground the specification, well, then you run into some issues. So yeah, there we go. So what are specifications actually? I guess show of hands, who has used PDDL in their day-to-day life? Oh, that's actually not. Only 4 people. Come on. Okay. Yeah. Oh, I in the back. So PDDL, it's a way of specifying, how, these kinds of formal transition systems, right? I have some state, I have some predicates, blocks can be on other blocks can be on a table, etc., things like that. And it's a really, it's a powerful way of communicating with a broad class of solvers that have been developed. And so, but it's actually really difficult to get LLMs to then generate PDDL that will describe your planning problem because, unfortunately, there's not exactly a lot of great examples of PDDL that exist. And they're much better at generating Python because they've seen a lot of really good Python. And so, there has been a lot of work on generating, PDDL domains or taking PDDL domains and generating them in Python or using Python as your specification language. And I think that this is, it's a rose by any other name, right? It's still a formal specification of the transition dynamics of the actual task level of your domain. Now, so kind of getting into what are the formal specs, talking about PDDL, I mean, if there's only 5 people who raise their hands about PDDL, I don't think, there's a lot of different extensions to this, right? There's a lot of things that these kinds of solvers can theoretically support in terms of if you're trying to do things at, with a formal solver, right? You can include things like numerics. You can do things like the global constraints, things that we're talking about right here. And most of these things only use the very most minimal set of predicates, actions, and things that, you can communicate with this. And I'll skip a little bit ahead. Not really going to talk about this, but I want to talk a little bit about if you're doing the kind of formal specification of, translating to something like PDDL. One of the reasons that people do that is that I'm going to call this in kind of a, let's say, pointing to the hardware lottery as a concept where, if you're not aware of this, it's basically, GPUs have won the hardware lottery because a lot of people can use them and have made very useful software for them. And so there's something I'm going to call the software lottery in terms of, why do people use PDDL to solve complex planning problems? Well, ICAPS formed this planning competition, and now we have really good PDDL solvers lying around that are able to solve really complex problems. But this is actually relatively, because, talking about what I was saying before, PDDL only can express certain things really easily. There's actually some things that are rather hard to encode in PDDL and things that are hard to encode in other kinds of specifications. So, also go take a look at that. Take a look at ICAPS. They're doing really interesting work over there. But, if all you have is this hammer, then you have to actually make, your nails so you can fit that. So I'll skip over because I'm getting told that I'm running out of time. There's another formulation where you can use something called SAT plan, where you encode your PDDL domain and your transition dynamics as a SAT solving problem. And there's actually a lot of really interesting work in this area. How do you efficiently encode these kinds of problems? And why might you want to do this? Well, if you can encode things as satisfiability or Boolean logic, then it's really easy to add constraints on. So now we can actually have much better communication back and forth, talking about how, why is this thing failing? Where is this, going wrong? And how can I efficiently enumerate different kinds of tasks, different kinds of plans? So now the robot can figure it out. And so there's this beautiful face of Neil up in the top right corner. But we did this basically. So it's like doing task and motion planning using SATplan, using an SMT solver and everything. But the idea is basically that you can kind of efficiently, you can see this really complicated kind of sliding-ish puzzle style thing on right. But this allows us to solve really complex geometry where the motion planning is going to fail most of the time. And this is because we can efficiently enumerate and we can put constraints upon our planning problem, or we can say, don't do this, I want you to try something else. And then we can go even further, where it's like, if we can do this optimization-based ground, there's actually a lot of interesting work in both optimization and SAT planning theory, where you can get things that tell you why things fail. So if you're doing optimization, you have IIS systems, the irreducible inconsistent subsystem. We can actually take that and we can extract, when we run that optimization grounding problem, it says you cannot place this block here because these guys are in the way. You need to move them out of the way first before we keep going. And then that's a really powerful concept, which allows us to solve these really complex geometric puzzles. And I think this can be applied in a bunch of other areas as well. And there's a similar concept in SAT and SMT solving called unsatisfiable forms, which tell you what are your constraints that are actually the problem that allow you to not solve your system. So, we can take this statement and then, going to advertise some of the work of my student Wei Hong, who I think is going to be at the poster session later. And so we can actually figure out what are the constraints that we're describing, right? And then actually translate this to the robot. So, here, because it's running out of time, current cast of constraints that we care about. So attributes, so these are kinds of the semantic properties. We have eventual, so, what do we want to be done in the end? Global constraints, things that we want to enforce over the entire trajectory, and then putting things that will actually sequentialize operations. We want to do this before that. And what we have is this LLM translation framework that allows us to go beyond just doing PDDL specification. And we've actually cracked open the SAT solver, in a sense, to provide a Python API that allows the LLM to say, okay, I'm going to enforce these logical constraints to hold over the entire trajectory or at different points in the trajectory. And it turns out, so here's an example of, we wanted to grab the red block and we wanted to not move the yellow blocks. So if you only have PDDL, this is really hard to describe. But it turns out, I'll skip ahead for time, that we can add in, we have the LLM translate the PDDL plus this augmented Python script to tell the SAT solver, oh, I actually want you to enforce the fact that the yellow blocks can never move. And so you can see it solves that. There's another example here. How do we do it? Looking at the time, don't have time to explain. Go talk to Wei Hong at the poster session. But it's a multi-step translation process. We'll go through it. Eventually it goes down to a task and motion planning solver. We do it on BloxWorld and some other types of problems. We have an ablation of our method and also the subtask style approach. And it turns out, I'm going to, you can read that statement. That's the type of thing we're asking the system to be able to solve. And I'm pretty sure I could ask Will or Neil, and I'm not sure they would be able to do it on their first try either, trying to hold all the constraints in their head. And you can see we actually get pretty, 60% success rate when subtask only reaches about 10. All right. So dirty laundry, some things that I want to bring up and some things that I want people in the TAMP community to start thinking about is explicit reasoning over uncertainty. So I don't know if you've ever heard of bomb in the toilet problems or anything like this. If not, you should Google it. It's a really interesting, kind of example of, how you have to reason about contingency planning, initial state uncertainty, and so on and so forth. And also it's like, is specification and traditional planning enough to handle everything that we want to be a robot to do? Is there some sort of, let's say separation where, we can do things more in LLM semantic land, more when we need actual hard specifications? There's also, how do we better support robot planning from the task planners that we're using? Like, I don't think fast download and SAT plan are necessarily the best use cases or the best, options that we have. And I think there's a lot of domain knowledge left on the table. And also, I think TAMP has been becoming a bit of a catch-all for a lot of different things. I think if more people could understand and describe the types of the properties of the tasks and the domains that they're looking at so that it's easier for us to understand and communicate with each other, that'd also be really nice. So in conclusion, constraints really powerful and expressive. And I think that they're going to be essential for, if you're designing these more, fluent and complicated systems. That's the lab website over there. And thank you so much.